something is amiss in our understanding of the universe. Cosmology seems to be heading for a showdown on one of its most basic questions: how fast is the universe expanding? For more than a decade, two types of measurement have been in disagreement. Observations of the current universe typically find the rate of expansion, called the Hubble constant, to be about 9% faster than predictions based on early universe data. Researchers hope that the James Webb, the most advanced telescope ever built, would help to settle the question once and for all, but consensus has so far failed to materialize. Instead, the Supreme Observatory has cemented the discrepancy with stunningly precise new observations that threaten to upend the standard model of cosmology. The new physics needed to modify or even replace the 40-year-old theory is now a topic of debate, an exciting and interesting possibility that there's something we don't understand about the universe. Join us as we dig deep into how new ultra-deep images from James Webb have just confirmed there is something seriously wrong with our understanding of the universe. Our universe started with a bang, the Big Bang. Energy, mass, and space flashed into existence all within a fleeting instant. Then, the young cosmos was formed, an expanding, roiling plasma broth of matter and antimatter particles that popped into existence only to annihilate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma should have consumed each other entirely, but scientists believe that some unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed the plasma pockets, squeezing and heating the matter so that sound waves, traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high energy density of the early universe's crowded content stretched spacetime, pulling a small fraction of this matter safely from the fry as the universe inflated like a balloon. The standard story goes, ordinary matter, which interacts with light, congealed around clumps of invisible dark matter to create the first galaxies, connected together by a vast cosmic web. Initially, as the universe's content spread out, its energy density, and therefore its expansion rate, decreased. But then, roughly 5 billion years ago, galaxies began to recede once more at an ever faster rate. The cause was another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the stretching fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our cosmos grew, its overall matter density dropped, while the dark energy density remained the same, gradually making the latter the biggest contributor to its overall expansion. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda cold dark matter, or lambda-CDM, model of cosmology, which maps the growth of the cosmos and predicts its end, with matter eventually spread so thin it experiences a heat death called the Big Freeze. Many of the model's predictions have been proven to be highly accurate, but here's where the problems begin. Despite much searching, astronomers have no clue what dark matter or dark energy are. As Ofer Lahav, a professor of astronomy at University College London, who is involved in galaxy surveys of dark energy, said, "Most people agree that the universe's present composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing fact is we don't understand the last two of them." But an even greater threat to the lambda-CDM model has materialized. Depending on what method astrophysicists use, the universe appears to be growing at different rates, a disparity known as the Hubble tension. Methods that peer into the early universe show it expanding significantly faster than lambda-CDM predicts. Those methods have been vetted and verified by countless observations. Therefore, as Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb measurement, said, "The only reason that I can understand at this point for them to disagree is that the model that we have between them is perhaps missing something." Measuring the universe's expansion takes a little bit more than a radar gun. The first method to measure this growth looks at the so-called cosmic microwave background, CMB, a relic of the universe's first light, produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump as the universe exploded outward. This soap bubble structure ballooned into the cosmic web, a network of crisscrossing strands along whose intersections galaxies would be born. By studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter and a value for the cosmological constant, or dark energy. Plugging these into the standard model spat out a Hubble constant of roughly 67 kilometers per second per megaparsec. A megaparsec is 3.26 million light-years. Let's pause on this number for a moment. If a galaxy is at a distance of 1 megaparsec away from us, that means it will retreat from us, and us from it, at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,340 kilometers per second and continues to grow exponentially from there onward. If a galaxy is any further than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheids, dying stars with helium gas outer layers that grow and shrink as they absorb and release the star's radiation, making them periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan Leavitt found that the brighter a Cepheid was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness and therefore gauge its distance. It was a landmark discovery that transformed Cepheids into abundant standard candles to measure the universe's immense scale. By stringing observations of pulsating Cepheids together, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. To build a distance ladder, astronomers construct the first rung by choosing nearby Cepheids and cross-checking their distance based on pulsating light to that found by geometry. The next rungs are added using Cepheid readings alone. Then, astronomers look at the distances of the stars and supernovas on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This gives a precise measurement of the Hubble constant. In 2019, the method was used by Rees and his collaborators, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors. According to the standard picture of cosmology, a vacuum had a super high energy density and repulsive gravity, causing it to expand. The more of it there was, the greater the repulsion, and the faster it expanded. In common with all things quantum, this vacuum was unpredictable. At random locations, it decayed into ordinary, everyday vacuum. The tremendous energy of the inflationary vacuum had to go somewhere, and it went into creating matter, and heating it to a blisteringly high temperature, into creating Big Bangs. Our universe is merely one such Big Bang bubble in the ever-expanding inflationary vacuum. Remarkably, this whole process could have started with a piece of inflationary vacuum with a mass equivalent to a bag of sugar. Conveniently, the laws of physics, specifically quantum physics, permit such matter to pop into existence from nothing. Of course, the next obvious question now is, where did the laws of physics come from? In 1918, German mathematician Emmy Noether shed light on this. She found that the great conservation laws are mere consequences of deep symmetries of space and time, things that stay the same if our viewpoint changes. A striking property of such symmetries is that they are also symmetries of the void, of an entirely empty universe. So maybe the transition from nothing to something was not such a big deal. Maybe it was simply a change from nothing to the structured nothing of our galaxy-filled universe. But why did the change happen? American physicist Victor Stinger pointed to the fact that as the temperature drops, water turns into structured water, or ice, because ice is more stable. Could it be, he speculated, that the universe went from nothing to structured nothing because structured nothing is more stable too? Why is there a monster black hole in the heart of every galaxy? There are about 2 trillion galaxies in our universe, and as far as we know, almost every one contains a central supermassive black hole. They range in size from monsters weighing almost 50 billion times the mass of the Sun to the 4.3 million solar mass Tiddler known as Sagittarius A** in the core of our Milky Way. But how they got there is one of the great unsolved mysteries of cosmology. We know that a stellar black hole forms in a supernova explosion in which the core of a star implodes, but nobody knows how a supermassive black hole forms. For most of cosmic history, the centers of galaxies have been where a lot of matter is confined in a small volume. It could be the case that one black hole started out as a small, stellar-sized black hole. As material fell in, it got denser and denser until it collapsed into a singularity. Maybe they were big from the start and formed via the direct collapse of a massive cloud of gas and dust. Maybe they formed in some other way, but nobody knows for sure. One thing, however, is certain: black holes are incredibly efficient at gathering matter. Not only that, they are also a likely solution to another puzzle of cosmology: how the first stars and galaxies came to be. It's hard to believe now, but there was a time in the universe when there were no stars or galaxies at all. This is known as the cosmic dark ages. Then something happened to light up the darkness and give birth to galaxies, stars, and all that followed. Observations suggest that there was a time when the universe was nothing but cold, dark, neutral hydrogen gas. How this hydrogen became hot, ionized, and ready to create stars is another puzzle. But one idea is that black holes played a major role.